Good day to everybody. Today is the 10th day of this refresher course with my 250 bright faculty members from India who are moving ahead in their dream path and have decided, of course, on going ahead with that empowering mantra which yesterday I shared with you all, of your own journey towards making a difference in this society and taking your path forward. Today is one of my most favorite day where I'm having a nice time to introduce to you all three smart, enterprising, young brigade of scholars who are definitely empowering the space with their hard work, knowledge, and dedication. Today we are going to talk about 3D technology, artificial intelligence. We are going to learn basics about it. And that is something, which I want all of you to understand. We all have been studying urban geography. We all have been studying the nitty-gritties of remote sensing and GIS, but here there are technocrats and scientists who are using this technology and are producing such a large database which any researcher would love to use and come out with great findings so that you all can contribute and make big decisions. I would have loved to call today my conversation with you all as lecture 0, because till now we have not talked about actually geospatial technology per se, but I just want you all to know that geospatial technology is where you capture spatial data, you store spatial data and a spatial data or the attribute data. You retrieve that data, you transform that data, and you also perform analytics on that data. And then further, you visualize that data or display that data in different forms. Here, there are these smart people who are using that particular database in real situations and contributing. We have Vaibhav Ghadiok from Hayden AI, United States, smart scientist with specialization in robotics, who would be sharing with you that how 3D maps are produced and what all they are being used in. Don't you feel, do you remember that statement what I shared with you yesterday? And all this while that maps are basically foundation visualizing tools of geographers. But are we there who are updating that knowledge and optimizing the usage of maps and using them in the right place, in the right form, in the right resolution, using right kind of data? And of course, even I'll say that, right kind of sensor too. Both active and passive sensors, are we using wherever what is required and then producing maps, 2D or 3D? Are we using LiDAR technology? Are we using artificial intelligence for the geoanalytics? And are our teachers, just like you and just like Shefali, who is right now in such a prestigious position at Indian Institute of Remote Sensing, And she's a group head of this outreach program of geospatial technology, which you all, can definitely join and upgrade your skill. Yesterday, when I gave you that mantra empowering, I said the first is, out of that thing that is there, is self-management. And in self-management, you have to upgrade your skills. So, ladies and gentlemen, and all my friends and all my co-faculty people, today is one of that day where I am going to introduce you to these three people, Vaibhav, Shefali, and Rahul, another young entrepreneur who long time back, who decided, who was just so that why do we have big fishes only making expensive software? And he designed, and he's the one who's been trying his hands with a lot of technology in his own way, and today is a part of industry. So we all have today in front of you these four pictures which are there. Two are the ones who are contributing in the industry. Geospatial industry. Using that spatial data, which we all geographers or geospatial faculty members in our curriculum should definitely have these things. But the key question is, are we having this in our syllabus? Are we teaching people in making use of it? Are we making our students who come for a supervision to do their PhDs? Are we pushing them that please make use of these particular database and visualize them in this particular way? So welcome. I am Seema Mehra Parihar, who you all know by now. I'm your convener of this refresher course. And I have definitely linkages with this particular place. Indian Institute of Remote Sensing, where I went to study in 1990. I have something common with Shefali again. She's the one, she's there at that place where I went in 1990. And then, of course, she's also done her further education from ITC Netherlands, where I went for my postdoc. Vaibhav is another young, enterprising person, a young, dynamic vice president who is got his basic education from India, and his designation is of Executive Vice President Engineering, Hayden AI, United States. He's an engineering leader with a track record of producing robotics technology. He has over a decade of experience in sensing, perception, state estimation, localization, mapping, navigation, and control of autonomous UAVs and mobile robots. Currently, he's an Executive Vice President of Engineering at Hayden AI, where he has architected the first autonomous traffic management platform to make our cities more efficient, equitable, and sustainable. Isn't that a dream? And this young boy from India has been the major architect of this first autonomous traffic management platform. Are we teaching our students all this in our curriculum? That's my key question. Congratulations, Vaibhav. I'm so proud of you and your achievements. Previously, also, the company that he was there, he co-founded a company developing navigation solutions with commercially available radars that match the performance of lidar-based navigation. Look at this. Today we talk about Atmanirbhar Bharat, and we all are talking about it. Vaibhav is actually doing that. At NATO, he conceptualized, spearheaded, and delivered a real-time collaborative HD mapping system for highly automated driving to one of the largest automotive OEMs in the world. And a decade ago, he's a young boy, but a decade ago, he also designed one of the first visually guided autonomous drones, demonstrating the first instance of autonomous aerial manipulation of the world. He has built robots that fly, climb stairs, autonomously navigate indoors, interact with humans, and dock with spacecraft. Vaibhav has published and served as a referee for top journals and conferences in robotics, controls, and navigation. Thank you, Vaibhav, for agreeing to be part of this course and sharing your own vision and telling this bunch of 258 uh, spatial uh, geographers, spatial scientists, geographers, and faculty members from different parts of India that, you know, today we have to move a step ahead. And you in this young age has achieved so much. Thank you very much. I'm genuinely obliged, Vaibhav, that you'd agreed to share and speak your mind and speak your different applications that you're doing with the urban spaces. Vaibhav is going to talk today of reinventing the future of safe and smart cities with 3D mapping in a short narrative. And and you will learn about it. You will see that what he's going to say. And reinventing the future of safe and smart cities. Don't we want the safe and smart cities? And Haiti and I has developed the world's first autonomous traffic management platform for smart and safe city applications. And so that's something which I'm not going to talk about. Neither I'm going to talk about that, that what is moving ahead and what is going to talk about it, because Vaibhav is smart enough, and I think so you all would like to listen from him. So, so you will come across his lecture as a first talk in today's learning space. Pay attention to it and learn about few words which are like, GNSS. We all know that global navigation system, and that which one he's talking about, how is he talking about, which platform is he referring to, and the 3D geometric maps, if he's talking about, does he talk about the level of the pixel levels and so on and so forth. So I would like you to make use of and make note of the real-time sensor data which he's collecting. Thank you, Vaibhav. And he's going to be your first speaker. And following Vaibhav, I was just debating, should I have Shefali as first and should I have Vaibhav as the second speaker? But then I thought, let me have Shefali as just the follow-up. Vaibhav is going to talk to you for 20 odd minutes, and then following would be Shefali. Dr. Shefali Agrawal, again, one of my most favorite person, or I should say one of my most favorite women in this geospatial arena, because I know that there are very few women who have made a mark, and Shefali is one who has definitely done it. She's a group head Geospatial Technology and Outreach Program Group, which consists of all the technology departments at Indian Institute of Remote Sensing, ISRO, Dehradun. She's a physicist at Indian Institute of Remote Sensing with academic qualifications obtained both in India and abroad. And as I said, in the institute where I've also been, she pursues her academic interest in addressing both fundamental and applied aspects of remote sensing, GIS, and allied spatial technology, with emphasis on satellite photogrammetry, LiDAR remote sensing, hyperspectral remote sensing, UAV remote sensing, underwater image processing, and advancing image processing related to land use, land cover, characterization, and vegetation physics dynamics. My question to you all is, do we have these words in our curriculum? In addition to her expertise, which she teach at IRS, she has many other accomplishments too in her professional career, and has contributed in various national and international projects, such as mapping and monitoring of land use, land cover, vegetation type across the South Central Asia for the first time from spot vegetation satellite data using spectral modeling under the European Commission program. And as I've already told you that she's presently a group head in the outreach. Points for new learnings, and you have to work with your skill enhancement. You have to be involved and coordinate in the different interlinkages. Here is this person, Shefali, who you will see she'll be talking at two different moments today. And currently she's engaged in 3D surface characterization and simulation through integration of satellite stereo imageries, terrestrial laser scannings, and UAV based data at IRS for natural resources and archaeology. They couldn't sustain that software, but he was very much a part of that. And his role is to propose the software-based solution to the business problems. Primarily, he worked on geospatial applications, which I want my all geographers to work here through. And the geospatial technologies, of course, we all know that have evolved, and in telecommunication, oil and gas, utilities, citizen services, municipalities, and health sector. However, in the age of artificial intelligence, the challenge is to make use of the new age technologies and opportunities and create new dimensions in the field of analytics and intelligence. And Rahul is going to show you all that today through his lecture on role of geospatial technologies in the age of artificial intelligence. Dear friends, through these three dynamic people, what I've done today is I have tried to tell you all that you all have to join hands, pick them up. And if you remember in that mantra, our relationships, build relationships with industry, with smart entrepreneurs, with those scientists, the ones who know the technology, and with people like Shefali and all those faculty member Institute of Remote Sensing or NRSC or SEC Ahmedabad and Go Ahead or even IARI. I'm your moderator, and my experience with remote sensing GI is of 33 years, and of course, made use in France and Tokyo and recently. Postdoc fellows, I've already told you that, and working on 2 research projects at the present using geospatial tools and technologies. One is, of course, for WHO, and another is for Department of Science and Technology. Besides, as I was telling you, that you all should definitely ask questions from Shefali. You all should find out about their outreach program. And as I was like, in 2019, they also awarded me with their award. So like you all can be part of it. You all want your API scores. Your institutions want to have a good NAC A plus accreditation. So you all have to be part of it. And remember, in case if Seema Parihar, who's just like you, can get 14 research projects, right from the Ministry of Women, Child and Development or Health or Science and Technology, you all can definitely get it and move towards it. So my request to each one of you is that enjoy today, enjoy, and these 3 great dynamic speakers. And of course, what I want you all to actually remember in this particular time is that you all should definitely pick up at least one of them as your role model. I'm very fond of each one of them. Today, I've given you 3 people, my favorite people, who have actually contributed in this arena in 2021 and will be there till 2000, in all those matching those sustainable development goals. So I am showcasing you, and in the dates to come, to those particular spaces which you all can capture by updating your skills. So in the process, what you're going to do is, through Vaibhav, through Shafali, through Rahul, what I want to tell you is, you can definitely empower yourself as a geographer, as a spatial scientist, and you can definitely empower geography discipline. Good luck to each one of you. Enjoy today's session. I think so it's going to be a lot of power-packed, dynamic section, which is going to expand your horizon and is going to further convince you that there is so much more to add to your knowledge system and skill enhancement. And if these 3 young people, and if Vaibhav can do all, going way back, to USA and, and to add value there, Rahul, fighting and sustaining and wanting to make a difference in this space, and Shefali giving them all a support with the foundation knowledge on 3D and artificial intelligence. Good luck for today's session, and I'm sure that you all would benefit from it, and you all would say, thank you, the organizers of the course. Thank you, Vaibhav. Thank you, Shefali, ma'am. And thank you, Rahul. And thank you, Seema.
Hi, I'm Vaibhav Ghadiok, the Executive Vice President for Engineering at Hayden AI, and I'm here to discuss reinventing the future of safe and smart cities with 3D mapping. Now, Hayden AI was founded on the premise of how do we make our cities more efficient. It is estimated that about 70% of the world's population will live in cities by the year 2050. Now, in major cities like New York and San Francisco, we do not expect the roads to get any wider. And yet, we need to transport 70% of the world's population through those streets. So if you reserve all the lanes for just cars, that might not be a sustainable model. Instead, what we need is lanes reserved for buses, for cyclists, for pedestrians, and of course for vehicles. Since each lane that is reserved for buses can transport 5x the number of passengers compared to a regular lane. Now, some cities took this to heart and actually created dedicated bus lanes. However, what we come to see is people coming in, parking in these bus lanes, blocking the buses, making them slower, which often leads to a decrease in ridership and also increased revenues for the MTA. This particularly affects a certain section of society that might not be able to afford other means of transportation, and leads to a certain kind of inequity that is often overlooked. Now, Hayden has created a perception system that can address these concerns. A perception system can be installed in any kind of a city fleet vehicle. This could be a school bus, a transit bus, a street sweeper, or a garbage truck. It consists of a compute module that can sit anywhere inside the vehicle, a front-end camera system that mounts behind the windshield, much like a dash cam, and might consist of between 3 and 6 cameras. We have an antenna that we install that gives us LTE, Wi-Fi, and GNSS. And of course, we can also access information from the vehicle through the J1939 bus, for instance. Now, as this mobile camera, smart camera, moves around the city and collects information, it is able to upload that information through Wi-Fi or LTE links to our backend to enable the building of what we call a 3D knowledge engine. All this data can be visualized on our portal. For instance, here we are visualizing a heat map of all the violations. The same portal can also be used to manage these devices and to update the software on these devices. Now let's have a look at what a device actually sees. For instance, in this case, the device is looking at the lane lines, understanding that there are multiple lanes, also understanding that this lane to the right is a bus lane. It's identifying a vehicle and a bounding box around it, also inferring that this vehicle might be driving in a bus lane illegally, and then going on to read the license plate of that particular vehicle to create a certain evidence package. We can do this while protecting the privacy of all the other vehicles here. Since we know what car is in violation, all the processing happens on the edge, we can literally blur out the license plates of all the other vehicles. Now, in addition, we do something more interesting to this audience. We're also trying to build a rich 3D map of the entire city. For instance, here you see we are tracking certain visually salient points to build a 3D mesh. Now, to this audience, the word photogrammetry might be more recognizable. Now, photogrammetry is often associated with certain aerial vehicles mapping the city in 3D. Now, one very important aspect of any kind of an accurate map is knowing your own location accurately. From an aerial platform, one can use high-end GPS systems and IMU coupled with IMUs, or high-end INS GPS systems as they're called, which can have all kinds of correction and up to 2-centimeter accuracy. These planes often have a direct line of sight into the satellites, often not having any obstructions. Whereas when you try to do the same thing, when you try to do photogrammetry on the streets, there are all kinds of obstructions. Knowing your location becomes a key problem. Now, we're going to discuss this problem a little later, a few slides down, but let's keep this in mind because this is going to come back again. So, coming back to what we are doing. So, as our vehicle barrels down the road, it tracks these visually salient points, builds this rich 3D mesh. With each successive pass of the vehicle, we can further densify this mesh, we can increase its accuracy, and we can also update the mesh. In fact, multiple vehicles can collaborate to form this mesh. But what good is just a geometric mesh? What good is a mesh where we do not really understand at an object level, at a semantic level, what is what? So in addition, now what we are rolling out is an ability to segment the scene at a pixel level. So here you see we're able to segment out a pedestrian from a vehicle, from a lane line, etc. And what we do is we take this 3D geometric mesh and cross-register it against these 2D semantically annotated images to fully annotate the 3D mesh. So now in 3D, we have this 3D mesh, which is fully annotated, where we understand that this part or these points belong to a building. This is a sidewalk. This might have been a pedestrian. You really don't want a mobile object to be part of your map, so I can throw that away. Or a car, for instance, again, you don't want that to be part of a map, and you can throw those points away, right? So essentially now you have this rich 3D map that's been fully annotated without any human intervention, right? In fact, what we can do is, since we have solved the hard robotics perception problem of understanding the environment around us, we can distill all this information into essentially a video game. Since I know there is a car parked at, say, position XYZ, another car parked at X1, Y1, Z1, tilted at some theta degrees, I can recreate the entire scene just like I could in a video game. And I can apply all kinds of use cases. Anything you can do in a video game, I can do that here, right? This could involve, much like the problem that I showed you earlier of bus lane enforcement. It could help with parking management. It could do asset inventory. Any kind of use case can be used here. Okay. That said, let's take a peek into the 2D knowledge engine. Let's take that as an example and see what is required to build these kind of maps with mobile devices. So the first thing, as we discussed earlier, it's really important to know where you are. So robust localization forms the base layer for any kind of maps. So how do we accomplish robust localization in, say, downtown San Francisco with skyscrapers all around us, or in Manhattan? So the trick here is to use a multitude of sensors to get you an accuracy of 20 centimeters or better, regardless of whether you're in downtown Manhattan or you're out somewhere in the middle of Iowa with direct line of sight to the sky. Typically, we divide these 4 kinds of sensors into 2 large categories: sensors that provide us relative information and other sensors that give us absolute information. So let's discuss the sensors that give us relative information, right? Those are the camera and the inertial measurement unit. Now, for the camera, it's a great sensor to understand orientation, to understand things at a very fine angular resolution of where things are. But what it doesn't do well is understand scale. A small object close by or a larger object much farther away project the same to the camera. So it really does not have an understanding of scale or how big things are in the world. The other thing a camera suffers as we do things like photogrammetry is scale drift, right? So if it starts knowing, let's say somehow magically it knew this object is 1 meter wide, by the time you run all your photogrammetry algorithms, as you keep running them, what you might find is a scale drift where it now starts believing it's actually 1.1 meter. And that is something that needs to be kept in check. The easiest way is to fuse various kinds of sensors and to take aid of other sensors to keep this drift in check. Another sensor that gives us great relative information, but at relatively short time scales, say on the order of a few hundred milliseconds, is an inertial measurement unit. It can often give us extremely accurate position, acceleration information, but again, on the order of a few hundred milliseconds. Anything more and it drifts quadratically. Right? Another issue with this sensor is the various kinds of noise that it's about 5 or 6 different kinds of noise that impact an IMU. And you are often unable to model each of them. We have mathematical models for 2 or 3 different kinds of noise, and then we try to control all the other kinds of noise by clever engineering. So these are the 2 main sensors that give us some kind of relative information about where we are, how are we moving in this environment. The other 2 sensors, which give us absolute information, are wheel encoders or wheel odometry that we can read from a vehicle's CAN bus to understand what is the absolute speed being reported by it, right? So it's looking at the number of rotations of your wheel, and we can identify what is the exact speed of the vehicle, which is an absolute metric quantity that this vehicle is moving at 30 kilometers per hour. Similarly, another sensor that we use is GNSS, in our case, multi-frequency GNSS, to enable us to tell accurate position, accurate time, and accurate velocity. Now, GNSS is often a sensor that is associated with position. The irony with this sensor is that amongst the 3 quantities, time, velocity, and positions, it actually is the weakest in providing position. It gives you ultra, a $3, even a $3 GNSS sensor provides you ultra accurate time. It's one of the most accurate timekeeping pieces that you can get for that kind of money. Similarly, it's able to provide you great velocity information. So we take this information and use it to cross-calibrate all our other sensors. So as we put all these 4 sensors together and fuse them in a mathematically coherent framework, we're able to achieve this 20 centimeters or better accuracy anywhere, anytime. Okay. So the second layer, once I know where I am, I can actually map and I can build real accurate maps and build object level maps, for instance, right? So in this case, let's have a look where we are essentially trying to map or to get the lay of the land, so to speak, to understand where are the lane lines, where is a crosswalk or a sidewalk, etc. And I'm mapping all those objects. And once I have this map, the next time my vehicle enters, it already knows where everything is. As long as it knows its position, it knows where everything else is in the environment. It is simply cross-checking against its prior information and potentially updating its prior maps or its prior understanding of the world. A third important aspect is providing semantics. So we are able to do a good job of understanding where we are. We're able to do a good job of mapping everything around us at a great level of accuracy. But often our algorithms do not have a semantic understanding of what is, for instance, this is a bus lane, etc. And it's often difficult to infer it automatically through algorithms. So for that, or for cases where we are unable to extract such semantic information purely through visual means or purely through machine learning, computer vision algorithms, we augment these with our own, what we call a route editor tool. We have a tool where we can mark up these maps saying this part or the rightmost lane is a bus lane. We might want to enforce it from, say, Tuesday through Friday, 9 a.m. to 9 p.m. All that can be done on a route editor. Any kind of semantic information can be added on this without needing to have sophisticated machine learning algorithms, which are honestly difficult to build with today's technology. We can put in all that information through our tool. So, and here is a little demonstration of that tool, and you can see how easy it is to mark up certain sections and then apply, for instance, in this case, some sort of enforcement logic. Again, this can all be done at a centimeter level, lane level accuracy of marking all this information up. So that begs the question, what else can we do, right? We were founded with this principle of making cities efficient or equitable. What else can this technology do? One use case, for instance, is promoting safety at bus stops, right? To understand if there are vehicles, for instance, blocking bus stops, etc. What has been seen is vehicles come in, block bus stops, impeding the ability for passengers to board the bus, which has often led to injuries, in some extreme cases, even fatalities. And with our system, for instance, if you see this picture where you're unable to tell whether there's a bus stop or not, since we have mapped the entire area, we can infer that there's a bus stop behind this car, right? And this car is probably causing issues or blocking the path of the bus. Another use case for us could be around counting passengers at a bus stop, for instance, right? So we can collect data in a completely anonymized fashion to say between 9 a.m. and 11 a.m. every Wednesday, we see there are 50 people waiting at a bus stop. Maybe the MTA wants to increase its frequency of bus service during those hours, right? Helping these passengers. Yet another use case for us is helping with parking management. What we see today with state-of-the-art parking management is something like this, a vehicle which looks much like an autonomous car with a multi-$100,000 sensor suite on top of it, scanning, being driven by a dedicated driver, potentially causing even more traffic and keeping track of vacant places, etc. Now, with the device, the kind of device we have built, essentially all this functionality is a software update away. We can simply click a button, update this, update the software, and start enforcing parking or determining if there are vacant parking spots and potentially notify the motorist around us. Another aspect of the technology can be around protecting the cyclists. Like I mentioned at the beginning of this presentation, we want to promote all modes of transportation, not just cars, but buses and cyclists. And this is another way where we can help cyclists and help hopefully protecting the cyclists. Here again, an ironic image where a parking enforcement vehicle, again, driven by somebody whose exclusive job is just doing this, blocking the bike lanes, right? They're trying to do the right thing by enforcing parking, by trying to make sure that there is equitable parking for all, and yet, unfortunately, blocking the bike lane and potentially making it really dangerous, especially in conditions such as these. Now, what we discussed was was the tip of the iceberg. The kind of platform we've built allows you to recreate the entire city in 3D in real time. So a city manager at any civic agency, for instance, can look at what's happening in the city in real time in a completely anonymized fashion. We are not compromising anyone's privacy. For instance, if we look at a pedestrian, we are not doing any facial recognition or gait analysis. It is simply pedestrian one for me, right? Now, let's look at some other use cases. For instance, there are cities that have asked us, hey, can you take a picture of a tree when you see one? Like, sure, that's a byproduct information for us, but why do you need it? Well, they need to know if they need to trim these trees, for instance. Some cities want to understand the intersection behavior, how many people are crossing a certain intersection, right? So as our vehicle comes to a stop, we can easily count the number of pedestrians that are crossing this, which can lead to better pedestrian design. It can help us time our traffic lights better, etc. We can also help cities with identifying certain traffic hazards, for instance, on the roads. So here you see a JCB, and we can easily detect this in real time and notify the relevant authorities saying, hey, there is this heavy object, it might be a danger on the streets, etc. Can also help with use cases such as asset management, where as a byproduct of a perception platform, we are detecting traffic lights, traffic signs, etc., fire hydrants, parking meters, everything. For instance, when we had a chat with the city of New York, both their fire department as well as the parking department were unaware of the number and location of the fire hydrants. Now, I let it leave it to you to imagine why both these departments were interested in fire hydrants. But again, they approached us, and this is an easy use case for us to solve for them. Further, we can help with use cases, as mentioned earlier, around parking management and curbside management. Now, again, the image that I want to leave you with in your mind is that of essentially a real-time 3D recreation of the city, and what are all the use cases that you can think of from there. Thank you.
Authentic, timely, and uniform information about the Earth's surface features and processes involved because of the changing climate, rapid development, and changing lifestyle. It has impacted the environment and its effect on the surface processes, and the features have gone to see changes. Now, this geospatial data basically combines both the location information, that is the latitude, longitude, coordinates of the Earth, and the attribute information, that is the characteristics of the object, event, or phenomena. And often, sometimes also a temporal information, that is a time domain, is also added to the location as well as the attribute data sets. Now, geospatial data can be both in 2-dimensional or 3-dimensional. The use of 3-dimensional is if we consider the use of 3-dimensional, which we will be discussing today, is of very significant, has a significant impact, or is a key factor, because the dimensions of the features on the Earth are changing constantly. Only scale varies. It can be from a microsecond to million years. So it's very, very important. The information about the 3rd dimension enables better and comprehensive understanding and helps in most of the decision-making process. I mean, it enables in an effective manner. So measuring the topographical information, or the 3rd dimensional, which is the height information, and monitoring the changes has a bearing on our understanding the coupled physical and biological chemical processes that shape our Earth. So what is required in this is what is the topographical, in requirement in all these processes is a high resolution height information, or the 3rd dimension information, in a temporal domain with a very, very high vertical accuracies. And if we talk about this 3D modeling, which we'll be discussing, or 3D refers to the process of creating a third dimensional representation of an object or the Earth's surface features. And this information is, as I said, is important for multitude of applications ranging from urban. For example, if I say in a city planning, as you all are aware today, majority of the cities face shortages of basic amenities like water, electricity, and space to live. The problem can be attributed to improper allocation of the resources available. So if we incorporate the third dimension information, that the height information in a GIS environment, it can help the government agencies, the engineers, to evaluate and analyze how certain changes in a city will look like and how these changes can meet the needs of the future generations. A typical 3D modeling, if you say in a city environment, would consist of a building information, satellite imagery, traffic data, which can be used by urban planners to find alternative solutions effectively and address the emergency situations in a very efficient manner. The other aspect is the building information modeling, which is again very, very important, and it depicts the real world settings of an environment. So combination of the building information model in a GIS environment would provide the necessary know-how, how to build a robust city model or a city, develop a city. So the combination or the 3D GIS or 3D model of a city can help produce error-free building management plans. The other areas which are there, again, it's related to urban development, is in the energy sector, in the location-based services which can be provided. Again, it requires a three-dimensional information. Then in case of disasters, navigation, relief operations during disasters, again required, especially in difficult terrains, in the hilly terrains. How to navigate the resources requires for water resources management, healthcare sectors. So again, another areas which is there, coastal areas. So coastal areas are important as they connect a country with the rest of the world for trade. So there are major threats and challenges for the development in the coastal areas, and it is important to recognize that all factors, what are the factors which affect the construction and preservation of the ports, the fisheries, the mining operations. Again, in these cases, you need the topographic informations. And so to do a better coastal management part of it, again, you require a third dimensional information or the height information, which is of paramount significance in those areas. So how do we capture the topographic information or the third dimension? One is there are various sources for capturing this information. One, we can capture from the Earth observation satellite platform. The other is the aerial platform, which consists of both aircrafts and the UAVs. And the third is from the ground platform, or using an existing topographical maps, which is also there, which can provide you can digitize those contours and create the third dimensional information. So as we see from here, the Earth observation satellites provide, I mean, they have a significant advantage. They provide a synoptic coverage with limited spectral, with large spectral capabilities, but the major drawback is with reference to the spatial resolution. So how high a resolution can be captured from a satellite. So maximum we have around 30 centimeters, but if you need something more than 30 centimeters, there are still limitations with the satellite platforms. Then again, the temporal frequency. So there is a limited frequency. They capture data in a temporal domain with a weekly or bi-weekly frequency, but if you need the data as and when required, again, there is a limitation. So in contrast to the aircrafts, satellites, aircrafts provide a high resolution. They may go around 7 centimeters, but are expensive, and the operations are susceptible to weather and the cloud conditions of the region. Then another platform which has come up in the last few decades is the unmanned aerial vehicles, which is the drones or the UAVs platform. So drones, they provide an excellent opportunity for capturing the third dimensional informations, and they lie somewhere. You can fly them between, I mean, they're at a lower altitude, so they are somewhere in between the satellite and the or the aircraft and the ground observations. So you can have resolutions up to 1 centimeter, and a very detailed topographical information can be derived from it. Then the ground sensors are there, which provide you very, very high resolution data with a very, very high accuracy, but they are labor intensive, time taking, costly, and difficult to acquire in inaccessible areas. So we have these different platforms, but as you can see from here, Earth observation platforms, we have the data which can be captured with different kind of the capturing mechanism processes and the wavelengths which have been used. We can have it in the optical domain with this near infrared or visible to near infrared. Then we have in the microwave region, and then the another way of capturing is the laser altimetry, which is again in the optical and the infrared region. Again, with the aerial photograph, you can have the images, and again laser altimetry. Terrestrial, you can have from the photographs with the laser. So we'll be discussing each of these techniques in brief. So you can see these are three-dimensional information which has been captured with either of these platforms and generated. So this is from the satellite. You get a very synoptic view of the surface. Then from the aerial or the UAV platforms, very detailed information, and from the ground, you are able to collect a very, very high resolution data sets of the third dimension which is created. So this is an aircraft platform. You can have aerial cameras with very, very high resolutions. Even from the drone platform, you can have high resolution cameras as well as the LiDAR sensors which can be placed on the drone platform, as well as the aircraft. From the satellite platform, we have, as I said, different wavelength regions. We can capture the data in the optical region with a multispectral camera. Then we have a hyperspectral camera, thermal sensors, but they do not give you the third dimension. They are giving you the thematic information, and the SAR sensors in the microwave region, which enables us to capture the information about the Earth in a different perspective, and also gives you the information on the third dimension. And in the optical region, you can have the LiDAR sensor placed on it. So 3D measurements from space, if I use the optical platform, the basic principle lies, if you have a single data and a sensor parameters, you can have only a 2D measurement. So you can only get the locational information and the attribute, but not the height information. But if I have a multiple photograph, so how the imaging from three-dimensional measurement from space is done, that you capture the data of an area using multiple images. So same area is captured from two different perspectives. So like similarly, what we do with our eyes, but we call it as a principle of photogrammetry, our eyes, there are two cameras. We can consider our eyes to be two cameras. So one, if I close one eye and look with that, I look at any object, and when I close and look with the other eye, the object seems to be displaced. So there is a slight shift in position, and this shift in position is due to the depth of the depth or height of the object. So using the same principle, I capture using the multiple imaging or the photography and the sensor parameter, we are able to capture the height of the object using the principle of parallax. So if we see, this is the nutshell how we capture the using the space-based platforms, whether it is space-based platform, what are the different techniques which are used to capture the third dimension. So if I have an optical data, which is using the visible range of the photographs, or the visible range to capture the images or the photographs, there are what we call them as stereo images. They are overlapping pairs of the photographs of the same area collected from a different viewpoint. So using the principle of photogrammetry, there are different satellites like Cartosat, GeoEye, Worldview, Iconos, QuickBird, which capture the stereo images, and processing this data sets, we are able to derive the third dimension. Then we can use in the visible region again LiDAR data sets. We have satellite-based platforms as well as ground-based platforms as well as aircraft-based platforms. But then we'll talk about how LiDAR points are used. LiDAR technology is used to capture the third dimension. Then we also have the microwave region, which uses the data collected in the microwave part of the electromagnetic spectrum, which lies between 1 millimeter to 1 meter. So again, there are three different approaches or methods by which we derive the third dimension. That is radargrammetry, which uses a similar principle like the optical data, capturing the image in the microwave region of an area with a certain amount of overlap. So different perspective geometry is used, viewing point is used to capture the same area, and uses the parallax. That is, parallax is a shift in the position due to change in the viewing position to generate the elevation model, or the height information is extracted. Then is the interferometric stars, which uses the data with different baselines. And then we'll talk about this technique where it uses the phase information which is there inbuilt in the SAR data sets to capture the height information. Then SAR tomography, that is the data is collected from different viewing angles and synthesized to get the vertical dimension, vertical resolution within. If I want to see the vertical dimension of a tree or a building, so vertical dimensional information can be generated using the SAR tomography. So this is the basic principle. There's a difference between photogrammetry and remote sensing. Remote sensing gives you the thematic information, what the land cover consists of, whether it's a vegetation, agriculture, water, what kind of thematic information is inbuilt in it. Whereas photogrammetry, it consists of the metric exploitation of imagery. That is, you are taking measurements, you're making measurements from photograph, whether it's the aerial area, height, planimetric measurements. So any kind of measurements which you are able to accurately make from a satellite, from the images, that is photogrammetry. And as I said, you use overlapping images of an area with a certain amount of overlap, which is more than 60%, is required to get an accurate measurements. So it started off with the French satellite Spot, which was the first one to develop cameras to take an overlapping images or what we call stereo capabilities from the satellite platform. And then onwards, we have the Indian satellite, we had the IRS-1C, 1D. Then from that onwards, there are number of satellites which have been launched across the world. As I said, from across India, we have Cartosat series across the world, Iconos, Worldview, QuickBird. They provide you with very high resolution up to 30 centimeters, varying ranges, but the highest is around 30 centimeters. And it provides you the third dimensional information, which is suitable for a large scale mapping using the remote sensing data sets. So I would like to say there is a difference between the height information which we extract is generally known as digital elevation model. There are another terminologies is digital surface model versus on digital terrain model. So there is a slight variation between them. So digital surface model, which is generally what we derive from a satellite-based platform, it represents the Earth's surface, which includes all objects on it, that is buildings, trees, etc. So it gives you the height. It doesn't give you the height of the surface of the Earth, but gives you the height of the object placed on the surface. For example, there is a building, what it will give you the height of the surface plus the height of the building, including that, or the tree. So this is known as a digital surface model. It gives you what we derive from a satellite-based platform is the digital surface model. Whereas a digital terrain model is required in many applications like hydrological modeling, even in urban applications, is a bare earth model, which is the height of the bare earth minus the height of the buildings or the trees or any kind of feature which is present on the Earth's surface. So here it represents the bare earth surface without the buildings on it. And as I said, for many geological applications, hydrological applications, even urban, where you want to plan the slope of an area for any drainage network, you need the bare earth height minus the building heights. So this bare earth height is generally generated from the LiDAR data sets. So either use it from the satellite platform or from the aircraft or the ground platform. LiDARs in general provides you with the bare earth, and your satellite-based platforms generally provide you with a digital surface model. But with using the processing techniques, we can derive the bare earth from the digital surface model. So, for example, high-resolution UAV data sets, they from that also, because the density of the points is so high, and using appropriate processing techniques, we can derive the DTM using the DSM when you have very high dense points or high resolution data sets. So these are few of the DSM derived from the Cartosat-1 data for different areas. So you can see the terrain information, how well it is represented, the height information which is there. You can see the mountainous region. This is a Shivalik range here, where you can see the topography of the hills is very well represented along with the drainage. So satellites have proven its capabilities in generation of this digital surface models with I mean, the resolutions of satellites, as I said, up to 30 centimeters. So it can provide you sub-meter level accuracy, and with a resolution of around 10 meters or so derived from these platforms, or even 5 meters when you have high resolution. With the Cartosat-1 with 2.5 meters, we could generate a 10-meter elevation model. So the grid size of these elevation model was 10 meters. So again, this is a comparison of different, as I said, different resolution plays a role. This is an Iconos data, which is a 1 meter spatial resolution. Cartosat is 2.5 meters. Aster is 15 meters. Spot is again 5 meters. So different spatial resolution and the kind of information which you see. So Iconos with 1 meter, I can get the height of each building. This is an urban Chandigarh area where you can see the height of each and every building could also be extracted, which is not possible with the Cartosat data of 2.5. So depending on the resolution, the kind of information one can derive is the capability is related directly to the spatial resolution of the satellite imagery. So this is again a comparison of how the information varies. So the first image which you see is a Cartosat derived 2.5 meter spatial resolution. And again, this is a 6 meter IRS-1C data, 5.8 meters if to be more precise. So same area, what kind of information is derived? So here you get a more coarser, but here you get a very, very fine detailed information derived from the satellite data about the topography. So higher the spatial resolution, better refined topographical information can be extracted. But if you want a generic topographical information about the globe or the earth for many applications, then you can use the coarse resolution datasets, which gives you a generic topographic information about the earth surface features. So this is again from this data, one can create the perspective view, so which is required in many applications. So this is one example of the Cartosat-1 when the disasters in the Uttarakhand happened. So pre and post landslide, one can create a real virtual 3D representation of the terrain, and then it can help in relief measures and to estimate the disaster loss, and send relief operations can be performed accordingly. This again is the Gomukh region of the Uttarakhand. You can recreate the model and do the planning applications accordingly. Now, again, this is for the Kedarnath region. So again, we generated this before and after the disaster, and how the disaster, one can understand the complete process of the disaster also, and relief measures, as I said, can be prepared or planned accordingly. From these high resolution satellite data, one can also extract the height of different buildings. So this is the campus of the Indian Institute of Remote Sensing, where we use this Cartosat data set to extract each individual building, the shape, the geometry, because the it also consists of the geometrical representation of the object, the shape and size of the object, along with the height information. So different high buildings which were there inside the campus, we could extract the height of the buildings along with the trees which were placed there, could also be captured from the Cartosat stereo images with the 2.5 spatial resolution. But then, as I said, the limitation is higher the building, better is the accuracy of the building height extracted. The size of the building is small. It's a single story. The accuracy is poor. If the building is multi-story, 4 to 5 stories, then the accuracy is higher because of the spatial resolution. If we had a higher spatial resolution, even the smaller buildings could be extracted with higher accuracy. Now, similar applications, which I said, we don't have an aircraft, but this is within a UAV platform. You can see the same applications, same processes, that is, you are generating or collecting or acquiring stereo images of an area, but we could collect the data with 14 centimeter, but we can collect it with even with the 2 centimeters or 3 centimeters. And this is the kind of topographical information which you extract. This is a fault which was not visible on the satellite data sets with the coarser resolution, but with high resolution data, this topographical geological information, which is a fault line, would clearly be demarcated and identified on this drone data sets. And a contour of 50 centimeters could also be generated. So here, if you see this is the orchard, mango orchard. So even the different canopy height along that, the contours could be generated, and you can generate a bare earth model along with the digital surface model, a very, very high resolution slope map, which again is required for multitude of applications. This is another example of the drone data which was taken for the landslide application. So there was one landslide prone zone in Nainital, which is known as the Balia Nala, and which is a very, very prominent landslide zone, and it impacts the area, the people living around it. So to assess this and to also help in the slope stability part of it, of the landslide, and also to demarcate the area, that if landslide during the rainy season is activated, which are the areas which will be impacted. Accordingly, measures can be taken to evacuate the people. So a 6 centimeter, 5 centimeter data was collected, and from that, the digital surface model was generated to be 6 centimeters, where you can see each individual building, the top, everything, even a chimney placed on the building, the height of the chimney could also be measured. So this is another landslide zone which is there, Naharkoti, where again this drone images were collected, and we could use it also in the modeling as applications of landslide, where one can estimate how much would be the sediment which will come if the landslide is active, what will be the speed of which the landslide debris will flow, and what will the area it will spread. So such kind of simulation activities one can do and estimate which are the areas which will be impacted by this landslide, and accordingly planning activities can be done for the to minimize the disaster loss. So this is a complete 3D perspective which looks like a real photograph, real model of the area, and this is the active landslide zone area, and these are the households which could be impacted, and once this is activated, so accordingly planning can be done, or warning can be issued to these people in these areas. So this is another applications of this high resolution DEM from the drone, which was very, very high resolution. One can estimate, do a quantification of sediment deposition. So it is for watershed planning, for agricultural applications, and even for river training applications in the high mountain zone, where the river changes its course because of a lot of sedimentation, how to manage and this river changing its course, or to stop that, you need a very, very high resolution topographical information which can be collected using the drone platform. Another of the applications of this height information or three-dimensional information is in damage assessment. So this is one of the images where we had both from satellite as well as from the drone platform of one of the monuments in Myanmar, which is a Sulanamani temple, and there was an earthquake with a magnitude of 6.8 which hit this area in around 2016, causing a severe damage to this archaeological site. So what was that? How much is the damage? How much is the damage was visible on the photographs, but how much was the debris, actual damage? To estimate that, both satellite and the drone platforms were there, but satellite has a drawback was that satellite has a certain viewing geometry. So because of that, and at the time of acquisition and the viewing geometry, there was a limitation. Certain areas could not be collected and there was a shadow. So the major damage which happened was in the shadow region. But drone, since you have the flexibility to fly it anywhere, anytime, so around drone images were collected and all from all directions, and same using the same processing techniques, complete improved damage detection. I mean, you could estimate the amount of debris which was collected, and accordingly, and also, I mean, precise measurements could be made about the damage, and it can help you even in the reconstruction of the damaged site, this precise information. Again, for stopping the illegal activities of query mining and all, in case of mining sectors, or this is an example of a sand quarry, sand excavation being done beyond the approved area. So using this high resolution images, one can estimate the volume of the sand which has been excavated, whether from the prescribed areas or from the unauthorized areas. So accordingly, you can see the kind of information, very, very high resolution information, is derived from the stereo images which has been acquired using the drone platform. Similar to that, underwater photography, even you can have, these are from the aerial platforms from on board the on the land surfaces. Beneath the land surfaces, that is in beyond the waters also, we can have these small underwater drones, or what they are called as remotely operated vehicle, to determine the bottom of the ocean topography. So what are the features between that? So this is the topography of a coral area. Similarly, there is an application which was there, that to find out any kind of feature which is there beneath the water surfaces. For example, the Dwarka city, which was said to be there. So one can have the images acquired of those areas to find out the features below the water surfaces. So same kind on from the land topography. So beneath the ocean topography can also be studied for many applications. So as we said, one of the platform we talked about was satellite. Similar to that, we have the LiDAR remote sensing. So this was developed way back in 1960s with the principle of light detection and ranging system, which is very, very simple. A LiDAR sensor is mounted on the aircraft or a helicopter, or any even satellites, aircraft, or on a drone platform. It generated LiDAR pulses, which are there in the visible range of the electromagnetic spectrum. And these is sent to the surface. So what we measure is the time in which the signal is sent to the ground. And once it gets reflected from there back to the detector, the aircraft, so what time it was received. So measures the time it takes to return from the source back to the aircraft. So what we are actually calculating is the simple distance is equal to speed into time divided by 2. So using that, one can find the ranges. So we calculate the ranges, and one range from the top will be different than the range from the bottom. So if we subtract the two ranges, we can get the height information. So using this, accurate distances are calculated to the points on the ground, and elevations can be determined along each surface building. So basically, that's what I said. It gives you the heights of the buildings to the ground. So the bare earth information can easily be recorded or extracted from the LiDAR data sets. So they fire a rapid pulses. So what you see, these pulses are traverses from the aircraft, satellite, or the drone platforms to the ground, and then get reflected back. So the time is recorded for sending and receiving, and using the simple equation of distance is equal to speed into time, one can calculate these distances. So basically the photogrammetry versus LiDAR is LiDAR as photogrammetry captures the stereo images. Here we have pulses of points. Photogrammetry, the accuracy gives you the digital surface model, whereas the LiDARs gives you more detailed information where you can capture the terrain, the bare earth information also. So the operating principles are different. So this is few examples of how space-based platforms or satellite-based LiDAR data can be used to estimate the height of the buildings or the height of the trees. The shape of the trees, the geometry of the trees can be easily captured with the space-based platforms. So this is using the satellite called ISAT-1, which is based on the same principle. So using that, one could estimate the height of the buildings. And also we can do a land use land cover classification based on the both the thematic as well as the height information in a better way. So adding the height information enables us to understand the features in a better way and classify very closely similar objects in with a much more better accuracy. So here, if you see, as I said, we can also capture the geometry or the shape of the vegetation features with the LiDAR data, which is not possible with the stereo images. So in this case, if you see, this is a mango orchard, and using the LiDAR data, we could easily capture the geometry or the shape of the LiDAR data set. So tree canopy height and the structures can be extracted, building heights, and even the water level, even minute level of measurements. So again, this is using the LiDAR data. We can find out the building shapes, sizes, dimensions, and create a virtual real 3D model of the urban built-up structures. So these are a few very high resolution LiDAR data from the drone platforms. Again, they provide you with very, very high accuracies. So LiDAR again has an advantage that because of high resolution, we can even map the power lines, telephone lines. So these minute details which are missed out from the photographic data sets or photogrammetric techniques, they are easily captured. These poles which are there, electricity poles, which is required for many urban applications, railway lines. So all this is easily captured with much higher accuracy and much more details with LiDAR data sets. So this you can see, it has a manifold applications in mining sectors, urban areas. You can create a complete 3D model with very, very high detailed informations. And it helps in, again, as I said, even the bridges which are captured, you can see from the drone data sets, these are the bridge, complete, it's recreated in the power lines, within the forest, it can penetrate a little bit into the canopy gaps of the forest. Again, the optical data has its limitations of it cannot penetrate those forest canopies, whereas LiDARs, if there are openings in the forest, it can penetrate and give you the information which is beneath it also. So these are, you can reconstruct the accident site using this, property development projects, wetland managements. So there are many applications where this high resolution LiDAR data can be utilized. So you can measure the underwater LiDARs are also there. You can bathymetry, which can measure the surface water depths, water qualities. So bathymetry from around a bridge foundation, you can see how this information is captured using the LiDAR data sets. Similar to that, the other technique which we are talking about is SAR data. Now, which is synthetic aperture radar, or the observations made in the microwave region. So unlike the optical technology, SAR has an advantage that it can see through darkness, clouds, and rain. And it's basically an all weather and is all weather anytime data sets can be collected. And it is because it is independent of light. It is an active source. It provides its own source of energy. And the principle again is the ranging approach, which is there with the LiDAR. That is, it transmits the microwave signal and then receives back the signal that are returned or backscattered from the Earth's surfaces. Again, it is measuring. So using the SAR technology, using the SAR data sets, there are three approaches by which the third dimensional information is captured. The one is the Radargrammetry, which is again which is similar to the optical stereo images. So we capture stereo data sets in the microwave region, and it provides you the surface cover in elevation information, and depending on the wavelength, because in SAR also you have different wavelength regions, which is from X band, C band, L and P bands. So depending on the wavelength, it can allows you to generate both DSM as well as DTMs. So if you use the lower wavelength region like the X and the C bands, it cannot penetrate the canopy covers. So it provides you more of a digital surface models. If you use the longer wavelength, which can penetrate the trees and the canopies, the buildings features, I mean, it has better penetration capabilities. It can provide you digital terrain models. Since most of the satellites which we are there in the microwave region, they operate in the short wavelengths, that is the X and the C bands. There are a couple of satellites in the L band. So mostly SAR-based height extraction from the satellites, they mostly provide you with the digital surface model. So as I said, one principle of extracting information is using this frame. You are capturing the image of an area from a different perspective, from two different locations, and using the stereo processing techniques, you can extract the height information. Other method is the SAR interferometry, which basically involves two or more SAR data acquisitions, which is collected from the same geometric configuration, same locations of the sensor over the same area with the small distances. That is what we call as a baseline. So the all configuration remains the same, but the it is captured with a certain distance, that is a baseline separation between the platforms. And to clear and what is the principle is, when you have two different positions, the SAR measures also the phase information. So there is a small phase difference between the two acquisition, and the difference in the phase is basically sensitive to the height or the displacement information of the Earth's surface. So these measurements of phase measurements, when you do, they are very, very accurate up to centimeter level and can be used for identifying areas of deformation from events like volcanic eruptions, earthquakes, subsidence. So all this can be you can use the SAR interferometry for this application of measuring very minute changes in the topography in a time domain, in a temporal domain. So these are few examples of these SAR interferometric applications of a Mount Fujiama, where the 3D information could be extracted with this interferometric technique by using the phase information. You have these fringes. These fringes are anyway related, as I said, related to the phase difference, and this phase difference is related to, it happens because of the height difference. So we can measure these fringes and then using mathematical formulation, extract the height of the object. So the SAR interferometry basically gives you, as I said, very, very accurate centimeter level of, or many a times when you have large baseline, different baseline data sets with differential interferometric SAR, we can have to millimeter level of accuracies. And it is very, very good for monitoring, mining areas where there is subsidence due to mining, or there is a subsidence in land due to groundwater depletion. So it is very useful from a space-based platform to monitor the land subsidence happening due to various reasons. So this is the land subsidence study over the Burgon oil field, where the interferometric SAR there are different approaches to interferometric SAR, different mathematical modeling to interferometric SAR, which was used to measure the land subsidence of, it was estimated that 10 millimeter per year was the subsidence or the changes in the land topography. So that kind of level of information. The other approach from the SAR is the tomography. And it has opened a completely new approach to how we look at SAR data sets. So tomographic surveys require, tomography, it gives you a complete analysis of the profile of the forest. Complete vertical profile of a vegetation or any built up structures. It provides you this kind of information. So for a tomographic SAR, we require, what you require is illumination data to be collected with illumination under different viewing angles to form a data stack. You have to have a data from different viewing angles, multiple SAR images of the same area, and using signal processing, you extract basically when you have data acquired from different viewing angles, they represent the backscatter energy in different, the energy from will be different. The back energy which is scattered in different direction is utilized in, and that gives you a third dimensional information. So you come to know about the complete vertical structures. So each scatterer is with different elevation information. So vertical, as I said, complete vertical profile of the vegetation can be extracted with the SAR tomography. So this is a SAR tomography. Using SAR tomography, the information extracted for the Berlin region. The third platform which we were discussing is the close range photogrammetry. Now, close range photogrammetry or ground-based platforms. Ground-based platforms are using ground instrumentations, whether you're using the photographs or using LiDARs. So generally, when we use stereo images or photographs, we call it as close range photogrammetry, because the photograph, the range is around, the distance between the object and the camera is less than 300 meters. So as you see from this here, that any object, you acquire the data from different viewing angles for the same object, but the position of the camera changes. So multiple photographs are acquired for the object. And as I said, overlap should be around 60 to 80%. You acquire a number of images and then process this image using photogrammetric approaches, and one can have a complete 3D reconstruction of the area, whether it is a building, whether it is a monument, for a landslide application, accident site reconstruction, or a 3D street view. Anything can be generated using these images acquired from any cameras. So this is one of the software which we have built. It's an open source software which can create a complete 3D street view from images, overlapping images, even acquired from a mobile camera. So even from your normal mobile cameras, I can collect the photograph of an area from different perspectives and process it and generate a complete 3D structure. The height information can be, so it gives you a georeferenced 3D model generated. So you can have the latitude, longitude, as well as the height information about the area. So again, this is using the same photogrammetric approach, imaging photography. This is a Buddha monument in Dehradun. So you can see a complete 3D model was reconstructed. This is a ground photograph, which was, and the images were clipped. These are the camera locations where the photograph was clicked and a complete 3D model was recreated. So again, this is for the Forest Research Institute. It's a very big building. So number of photographs which was clicked, they had across the entire area. So multiple photographs were taken. So around 56 photographs were captured for this building and was reconstructed. Similarly, we did an exercise for a landslide monitoring. So pre-monsoon and post-monsoon photographs were collected. An amount of the debris which was flown out was measured using these high resolution photographs. So even for landslide monitoring, this can be applied. So this is a 3D street view, which was generated with a mobile camera photograph of an area. So 3D information. So this was one of the case study where we could also use this close range photogrammetry where it is inaccessible to go and you want to do immediately a survey from a distance. One can capture the photographs if it is accessible, you can have multiple photographs and we can create a complete 3D model of the area with a complete database kind of what kind of built up structures are there. And in case of any kind of flood which happens here, I can estimate or do a simulation which are the buildings which will be affected, and we can assess the damage, and accordingly mitigation measures can be carried out. So this is using the ground photograph. One can create a completely 3D model of the object, built up structures or the urban areas. So again, from the ground platforms, we have a terrestrial laser scanner that was using the photographs either from a camera or from a mobile devices, any source where you have multiple photographs. But this is using the LiDAR, which requires a very sophisticated instrument on ground, which is known as a terrestrial laser scanner, which again uses the ranging principle. So, but this gives you, again, I said, since it uses the laser pulses, which is in very, very high density. So it gives you very detailed, dense information about the objects on which you collect the data sets. So this is, if you say in a building, very, very minute information could be captured with the laser scanners. So here again, we could use it for landslide monitoring, for estimating the tree height, for in case of the close range photogrammetry, this minute details could be missed out, but with the LiDARs, these iron railings and the carvings in the iron railings can be very well captured and can be used for heritage site documentation, and for if any kind of damage is there, you can use it for reconstruction of it. So this is for the Buddha statue. So complete reconstruction, or you can say each minute, if you zoom in, you have each and every information available about the area. So this is a combination of both the close range photographs, stereo photographs, as well as the terrestrial laser scanner data to capture the engineering asset of the structures. And even we can say if there are changes over the time, if there is the changes in the bridge structures, how it is. So for the maintenance of the bridge, this data can be utilized. So it gives you very, very high resolution information from both the close range as well as from the laser scanners. So you see a complete 3D model can be generated, and you can tilt it from all angles and see the information which is there. So it's a building, this is a bridge in Hardwar region, which has very, very finite structures here, the ropes, which can be easily captured with a terrestrial laser scanner. So similarly here, a very old bridge, and the whole structure has been captured. This slide illustrates an application of 3D GIS for estimating damage in vulnerable built-up areas on slopes susceptible to collapse by integrating two techniques, that is using close-range photogrammetry and terrestrial laser scanning. Since the study area was very small, that is around 2,900 square meters, and the variation in the slope was so subtle, it was not very large, very minute slope was there. Hence the conventional approach, that is the use of satellite-based observations, which has a resolution, the medium resolutions, even with the higher resolutions of 50 centimeters, we were not able to capture these subtle variations or in the elevation. It was difficult to estimate from the satellite-based platforms. So terrestrial laser scanning was the instrument which was then kept on the ground using the point clouds, sending laser pulses. It was used to generate a surface model with a very, very high point density. And this surface model was taken as a prime data source for simulation of a debris flow model. So that means to simulate if there is a landslide, then how much amount, with what amount of, with what velocities the debris will flow. And then close range photogrammetric data that is the photographs which was acquired from multiple acquisition points using the photogrammetric approach was used to generate a 3D building scenarios using these overlapping geotag photographs, and the correspondent databases was attached to the individual buildings. So the height of the building, the location, the number of stories in a building, everything was attached to the each individual buildings which is there. And then a modeling approach was used to develop to model the amount of the debris flow and the speed with which the debris would flow, and what are the risk zone areas, which are the buildings which will be affected, to what areas this debris will flow, and what will be the regions which will reach. So close range photographs resulted in aggregating all the data pertaining to the buildings, to the reconstruction of these photo textured models of the built up areas, and with sub-meter level planimetry accuracy, as well as the elevation that can be visualized. And this can be visualized, I mean, this entire model can be ported onto a geoportal platform, like we have a geoportal on Bhuvan. Bhuvan is our geoportal where we can upload this complete scenario. And it generated 3D buildings with the associated databases. And this entire 3D database was used in conjunction with the debris flow for estimating the risk zones. So the technique developed can be an effective method for identify potential risk prone in the built up region, in the high mountainous region where they are susceptible to such kind of disasters. So it can be used for even in the flood simulation case, where you can use this kind of data for simulating the damages or the areas which will be affected by the water level variations, can be used to simulate the flood scenarios. So based on one's need and accuracy requirement, one can use either the photogrammetric approach, which uses stereo photographs or images which are captured from multiple acquisition positions from either the satellite-based platforms, aircrafts, or drone platforms, or even the ground-based platforms. Now, the satellite-based platforms provide digital surface models, whereas the drone-based platforms, which are on a lower altitude with a 1 meter to 2 centimeter spatial resolution data sets, can provide you with very, very high resolution elevation information, which can help in generating the digital terrain model. So besides the surface model, it can also help in creating both surface as well as digital terrain models. Now, globally computed digital surface models for the entire globe, even for our region, derived from optical based satellite, that is, it's a Japanese satellite, Aster, is available. And also another data globally available TEM from the ALOS, which is again is a Japanese satellite, is freely available at a spatial resolution of 30 meters. So one can download for any region this 30-meter based derived digital surface model for your own area and use it for further applications. One can use even if you want a very, very high resolution model of a region, or for the urban applications where very precise is required. So one can use a 3D point that is generated from the LiDAR sensors. And this again, LiDAR sensors are also there on board the satellite platforms, but there are very few in number. There's a couple of them which is available from the US, which operates in this using this LiDAR technology. And the LiDAR point densities is also not very large. It is scattered, but the information, height information derived from these LiDAR points, though it is in a scattered manner, it's very, very high. And one can integrate this information along with these stereo satellite images to improve the vertical accuracies or the measurement accuracies of the satellite derived DSMs. Also, these LiDAR sensors are available on aircrafts, but this is again limited. Each country has its own way, but one can also use the drone-based LiDAR sensors to give a very, very dense point cloud, creating a high-res accurate DTMs. So the advantage of LiDARs is it can provide you directly the DTMs. And also you can use the ground-based platforms both in the stereo modes as well as the LiDAR mode. So using just a simple photograph images collected from a camera, any kind of a camera, and even the mobile phones using appropriate softwares, photogrammetric processing, one can generate the 3D model, or using the terrestrial laser scanners, which is a ground-based instruments, which again provides you very, very high dense point cloud informations. So SAR data, I mean, this TLS, we can very, very high resolution data sets can provides you two create detail in such a minute manner that it can be used for even archaeological applications, where the carvings, the structures, everything is captured, and you can create a complete archaeological documentation or archaeological databases for future use. Now, another approach which we saw was use of SAR data sets, that is the data collected in the microwave region, which is a longer wavelength. And there again, you have both the approaches. One approach is using the stereoscopic or approach, that is using photograph or the SAR images collected from different acquisition positions, like, and the photogrammetric processing can be used. But however, the accuracy of SAR in this mode is limited. But to get the full potential of SAR, because SAR also records the phase information, and this phase information is related to the height. So you collect the data with different phases using, and then using the interferometric SAR technique, one can map the topographic variations, even at differential interferometric SAR or permanent scatterer interferometric SAR, one can map the topographic variations up to a very minute scale, that is in the millimeter level. And this can be used for various applications, topographical, for surface motion detection, various geological applications, land deformation studies, and subsidence studies, specifically in the mining areas, and also subsidence due to groundwater. So whatever. So global derived DEM using SAR based technology is also available. So one of the derived DEM using shuttle radar topographic mission and interferometric SAR based on the technique of interferometric SAR, and from another satellite. This SRTM is from the US, and then the Tandem X satellite is also freely available for the entire global region for one to download. The other approach to generate using SAR is the tomography, using SAR tomography, which give you a complete vertical structure. So specifically in case of forest and urban applications, one can use SAR tomography for getting a complete 3D profile of or complete vertical profile of any particular building or for a tree. Or one can use a synergy of any of the techniques, whether satellite, air or ground, whether SAR or optical together, to get a better understanding of the terrain. So a synergy can be used. For example, this slide also is showing a synergy between the close range photogrammetry and the terrestrial laser scanning. One can have a synergy between optical satellite photogrammetry and SAR based interferometry. So you can have wherever each of them have their own strengths and shortcomings. So wherever the shortcomings there is a strength of the other. So one can use combination of this different technologies to get a better information about the terrain. So 3D data and 3D modeling coupled in a GIS environment has a tremendous potential. That's an application in wide range. So not only for understanding the environment, for the very natural resources applications, but it also finds its applications in a large number of areas, a variety of areas. Like it is used for building. I mean, nowadays it can also be used for building machine learning systems, especially deep learning, and also to have an improved terrain or land cover classification. One can also use it to create a virtual reality model, and this virtual reality model can be used in various fields. It can be used by the car industry for enabling a better decision making in the urban environment. So it has found applications, there is a lot many applications even in the entertainment industry. Virtual reality can be used. So this 3D models or 3D photographs is also used in the field of medicine to understand the human systems, and then the doctors can diagnose a disease in a better way. So complete 3D can be generated of the body internal parts, and then he can perform or diagnose and they appropriately treat the patient. So and space-based so the data sets provided can be from space-based platforms coupled with ground sensors, or with air-based sensors. Now drone, which has come up with the latest technology, can provide a very highly accurate topographic information, which can be used in wide variety of applications in different fields. So depending on that, depending on your application accuracy requirement, you can choose between the techniques and the set of data sets which you would like to have, whether it is a photogrammetric approach, LiDAR point cloud, or SAR data sets, and appropriately amalgamate all those data sets and generate a good 3D model for application of your choice. Thank you.
Hello everyone, my name is Rahul Thakur. I'm going to speak on geospatial technologies, and the topic of this video is role of geospatial technologies in the age of artificial intelligence, and also its impact on the social and physical aspects of our day-to-day lives. So before I get into this, let me introduce myself. I am working in the software industry for more than 20 years now, and I had been working on the architecture of the applications. Mostly my role is to propose the solution of business problems. Primarily, I work on geospatial applications, and I have been doing a lot of research in this area recently. So let's begin with the subject now. I assume that we know what a geospatial technology would refer to, and we already probably be understanding a lot of things around geospatial applications, how it is used in the software industry and other things. That is one assumption that I would make in order to get into the deep dive of what I'm going to cover based on the experiences I have had while working on these applications. So I'll start with the current state of geospatial technologies. What is the current position that we have in terms of the geospatial applications in different industries? And we had been extensively using these applications in telecommunications, municipalities, utilities, mining, transportation, shipping, and people have been using in citizen services applications. And there are a lot of other applications also. We already know that Google Maps had been playing a very dominant role in terms of the navigation. So telecommunications use it for network feasibility, their inventory management, their field service. Municipalities, they use it for multiple applications. Some primary applications are their land records management system and their works management, wherein the contractors would place a request for a tender, and for example, they have to dig an area. They can create a polygon in the GIS application, and then submit, and there is a complete workflow which is completely based on geospatial technologies. Then there is an approval process, and it goes through all these steps, and things are approved. Similarly, it is also happening in the utility sector. For example, electricity departments, the gas line departments, they had been using these GIS technologies a lot in tracking their distribution network and their assets. For example, what wires are being placed underground or probably over the poles. So they have that complete network being mapped onto the system, and it goes same with the PNG pipeline gas networks. Also, they use the similar technology, and they track everything. They basically troubleshoot whenever there is a problem that comes in, and it is being extensively used by utilities industry. Then mining, they had been tracking their consignment. They track their vehicle, how the delays have been there. So if a driver is taking too much time in a single place, probably he may have any problem. He's contacted, and that's how transportation industry has been extensively using it. Then citizen service. So since a lot of areas are now becoming smart in terms of the city planning, and they had been making extensive use of software applications, and they also use these geospatial technologies in their, for example, emergency response system, their crime control system, traffic control system. And then this is a new concept which is called social listening, wherein for example, a police department would be listening to what people had been saying on Twitter, Facebook, and other social media platforms, and it's all a smart system which basically gives analytical feedback to the people who are using these applications, and it is also helping a lot in terms of control of the citizens. And there are other industries also. A lot of small businesses even are using it for their sales and their marketing and field services and a lot of other things. So more and more, what I would want to say is this geospatial technologies have now evolved. They are already being used extensively, and it's made a lot of it's covered a lot of ground in terms of software industry, to the extent I know about it. So now, when we already have made a significant contribution, so what is the next thing? Now, as we all know that this is the age of artificial intelligence. The AI is rising like anything. We are seeing artificial intelligence everywhere. It's been everywhere. And then machine learning, it has been extensively used now. We see it in all the sectors. People are doing data processing like anything, and they're generating a lot of data. That's what is happening in the software industry. And we know what Facebook is doing, we know what Twitter is doing, and we know what Google is doing. They're now becoming much smart with how much data they can process. And as they process the data, we have now larger and broader pool of data sources available. We have a lot of data now. It's something that we never knew of. Now, for example, data is coming from social media platforms, and there are different types of relationships that have been now established. People are doing a lot of exciting things using these opportunities. Also, it's not limited to the structured data, the traditional data which we had been seeing in form of rows and columns. It's more than that. Systems are now able to understand the pictures. They can read from pictures. They can read from videos. They can listen to the people, and they can generate a lot of data out of the voices, the dialogues. There are dialogue APIs, there are computer vision APIs, and it's generating a lot of data again. And this cloud computing is giving us a lot of opportunities now. It's very much scalable, and so people can do better data processing. They have now access to more computes, better resources, and it's all on demand. You can scale it anytime and then shut it down when you don't use it. And this is also giving us a lot of opportunities. So geospatial technologies are now have a challenge, and they've accepted the challenge also. They are using extensively this machine learning. These availability of data resources is also something they are taking advantage of. And all these things that have come up now, geospatial technologies are making use of all these things. And we are moving forward to offer better solutions based on these options that we have in hand. Now I'll talk about one lab story. We did a project for a jewelry chain, and this was one of the example wherein we can clearly say how geospatial technology contributed to something which was not possible otherwise. So the jewelry chain wanted to optimize their sales, and they wanted to predict where they can create a new store. So what should be the best location for a new store? Whenever a new store is started, it is always a challenge to identify that location. What would be the best location? And secondly, they also wanted to identify the target that should be assigned to a particular store. What is the best sale figure that a particular store can touch? Now, the thing that they have with them was their sales data, historic sales data. They had it, and then they also had the addresses of store. That was very obvious, but nothing would have come out of it because simply these attributes would not be able to do anything in terms of the prediction. So again, we wanted to use machine learning, but we did not have anything that could have predicted the location and probably the target sale. So we did not have those variables available. So we started using geospatial technologies to get this thing done. So we accepted the challenge, and what we did now was we started preparing the data, and immediate first thing was to geocode the addresses of the stores so that we have the longitude and latitude values. I believe people understand what geocoding is. Basically, this is the process of converting the addresses to the longitude and latitude values, which can be plotted on a map. And based on these longitude latitude values, the geospatial analysis can be done, and we can do multiple things. So we can identify the relationship between the information that we have in the sales data and then also the other data that we may have in the GIS applications or probably the geospatial technologies. So after we completed with geocoding, we could plot those stores in the map and then create the buffer of all the stores so that we can identify how much area a store can cover. So this was again based on research. So once we had this, we divided the demographic data which we have from census, which is being collected by Census of India. So we had that distribution in the grids of 200 by 200 meters. So we did the overlay of these stores on top of those grids wherein we have the demographic data. And that's how for each store we knew how much population a store is serving, how much male population, what is the age group of the population, gender, and we had all the information available now. So once we did that, we started identifying the correlation between sales and also demographic fields. So we did it one by one for multiple fields, the population, just to check whether the increase in population also leads to increase in sales. But there was very interesting observation. We did the box plots, but what we identified was the increase, I would say, of the sales of stores were directly proportional to the increase in the population of women above the age of 60 years. So this was a very interesting observation. So based on this, we were able to identify that women above the age of 60 years are basically influencing the sales of the jewelry stores, and this came out as a very interesting use case for us. Anyways, since we had all these things plotted, we had known the shadow zones, the basically empty areas, and we could based on the areas wherein the female population and probably the female population above 60 years. In fact, rather we had a good correlation with the female population between 40 to 60 years. So where these population was more, we could have identified that this basically is the area wherein the new store can be placed. Then we had the peaks. At least we were able to remove some outliers though, but we knew whenever there was a peak somewhere in terms of the sales of the store, and we were able to identify based on those higher sales, we were able to identify what could have been the potential sale of the store, what targets should be assigned to the store for the sales. So this was very interesting use case. Now, what is the future of the geospatial technologies? We know we are soon going to have the drone-based deliveries. So we had been doing geocoding, and there are a lot of research being done to identify the location within a building now. So three-dimensional geocoding is something that can be the perk of future. People are working on it already using IoT. They're trying to identify within a building where the address is located, or probably a person is located. That's what has been happening. Then the routing and navigation based on health and safety. There are systems which are now able to identify the safe routes. For example, the routes wherein there is lesser pollution, and people are working on it extensively, even though it is more on the research side now, but people have been doing it. There was some work being done to identify in the time when we were facing a lot of problem with this COVID-19. There was some safe zones which were identified, and based on that, safe travel was identified. So this is what people had been doing. Again, this is more of a research item now, but soon it will be a reality. Then also the determination of suitable area to live based on the age, gender, or probably the health details. There would be the systems wherein you will be able to specify your biodata, and you can upload your biodata, and then the system will be able to tell you, yeah, this is something where you should find your residence. There can be happiness index also involved in such things. So these are few applications which people are already working on. There are a lot of other areas people are working on. For example, now there are systems which are automatically trying to digitize the maps, the vector maps from the raster maps. The system are trying to do it, but even though, again, this is one of the research thing. People have been trying to identify the building polygons for the geospatial analysis automatically from the satellite images. This is what people have been doing. They are trying to identify the heights. Then some telecommunication companies are doing the change detection to identify where their towers might be blocked by a building, or probably again a hoarding or something. They're creating those automated system which can tell them, saying that see, you placed a tower here, but now since you have a hoarding being placed on the top of this building, and this is something that has come up in my last scan, so you should reconsider your network. So those kind of systems are being worked on. People are extensively trying to do this. Then again, some fictional things like use of geospatial similar technologies in the study of space. Fiction would be the future of tomorrow, and maybe reality of day after tomorrow. So we never know when things like these will be used. Coming back to the lab story, that actually explains how geospatial technologies are giving us the idea of how women have been playing the important and dominant role in the purchase of jewelry. It explains the power of the women, how they influence, and the fact that the new stores would be defined completely based on the women population. It's not just the jewelry. There can be multiple domains wherein such things will happen. Now, again, coming back to the social media analytics, that is also one of the spaces wherein the geospatial technologies would be impacting the social spaces of our lives. Again, coming back to the health factors, there also geospatial technologies are going to play a major role. They already are doing it now, and they'll do more, I believe. So with this, thank you very much. I'll wind up this video here, and thanks for your time. Have a wonderful day.